Thanks for the introduction. Thanks for the organizers to invite us. So the talk is about joint work. It's not only my work, of course. So it's all our team work. So it will be like a very diverse topic, all relative to attacks, vulnerabilities, and defenses of collaborative learning. So I have quite a lot of slides. I don't want to be too long, but so if you have questions during the presentation, do not hesitate to ask them. I have different sections at the end of a section, because if we wait the whole presentation, I think it may be a bit out of topics. So if it's possible for the organizer, I would like to have a question during the talk. So we stay in the topic. So my name is Héliou, and I work at the research in computer science labs of Thales, that is called Cortex Labs in Palaiseau, so very, very close to Paris. So I'm in a team that's called Friendly Hackers, and what we do is exploring AI vulnerabilities. So there is like plenty of them, very diverse kind of vulnerabilities. From data poisoning that was presented and by Katarzyna this morning, to backdoor evasion, injections, and different kind of model and data theft. And we do this kind of work in order, of course, to design then better countermeasures, or also to assess the vulnerability of the model we have, in order to be able to export them, to sell them, knowing what are their weaknesses. Okay, so just quickly presentation of my project team. So we are 10 people, led by Katarzyna Kapusta, work at Thales also. We have different background, from data science to more cyber security. And our purpose is to enrich a battlebox library that contains different attacks and defense mechanisms for AI. So we do like red teaming and blue teaming attacks and assessments. So we work with other teams in Thales, and we're also contributors to European project Horizon, FED, and Confiance.ai. We love to participate to different challenges. We won 2 challenges in 2023, and we usually participate to several challenges when we have some time to work on them. So as for the presentation, so there are 4 main sections. The first one is regarding confidentiality and privacy. So 2 kind of attacks, membership influence attacks and model invasion attacks. Then there will be the ownership and traceability. So how can we prove it's all regarding IP, so intellectual property? How can we prove that a model is ours? So to do so, we have watermarking, but there is also always a duality between the attacks and assessments. So watermarking can also be seen as backdoor if it's not legitimate. And then there is the ethic and right to be forgotten. In this section, we'll see machine unlearning. So how can we unlearn some data? How can we prove that the model is not linked anymore to some instances of a data set? And then bias assessment and bias mitigation for the data. And finally, model robustness and adversarial attacks. That will maybe be like a transition to the next presentation, that is, if I understood well the title, regarding robustness of machine learning. Okay, so we'll start with confidentiality and privacy. So there's 2 different attacks that we will see here. So it's membership influence attack. So Alexandre just explained it, but I was just going to rephrase him. So here the aim of the attacker is to predict whether particular data was or wasn't in the training data set. And usually when we use it is just to measure the privacy level of a model. So it's like kind of blue teaming, meaning that we have trained the model and we want to assess whether our model is going to leak some information regarding the training data set. And there is the model inversion attack that is more like a real attack, where the attacker wants to reconstruct training data using the model. So on the right, you can see like a picture that illustrates the different kind of attack. On the top is the membership inference attack. So we are going to want to assess whether data was part of a training data set or not. And on the bottom is data extracted from a machine learning model. So we started to really work on it in 2023 with a use case that was a challenge that was proposed by the DGA. So they provide a model that was already learned, and they explained that the model was learned in two steps. So in the first step, the model was learned using 41 classes of a dataset that is a public dataset, of course. And they, in the scenario, they have written 11 of those 41 classes were sensible. And so they try to forget these classes. And to forget these classes, they remove them from the training dataset and add 10 other classes in the dataset. And this leads to a final version of a model. It's here on the green. And then when we were asked to assess which data was part of a training dataset and which data was not part of a training dataset. So that was very nice to be part of a challenge, because it was the first time for us that we were like ready, like the red team, because we didn't train the model and we have no idea how the model was trained. It was still a white box attacks. White box means that we had the model, so we had all the weights. We had also the data, so it's like very weird settings for membership inference, but it's actually a setting that is working. So we had the dataset is public, so we know the dataset. We don't know, of course, which data was used, but we know the classes, we have a model, and then the idea was to do membership inference attack and infer which data was used and which data was not. That was the first task. The second task, I will re-explain it later in the presentation, was unlearning. So here our job was to find the classes that have been unlearned. So the 11 classes that was used at the first step of a model, of a training process, and then that have been unlearned, the aim was to find them. Okay, so that was quite a difficult task, but finally we won the two tasks. So we had but it's only like friends challenge. It's not like a huge challenge like Kaggle, but it's still quite nice to win it. And our solution was to train multiple what called shadow models. So it's a model that are going to mimic the behavior of a targeted model. We learned the model on the public data sets. And the intuition is that if we manage to have like a lot of diversity in the shadow models, and they all behave similarly to the export model, then one of them is going to be very similar to the export model. We train thousands of models with different settings in the training procedures. And then we compare the shadow models with the export model regarding to the data to predict whether the data was used or wasn't used. So that was the first time that was the first time we really like design our own membership inference attack and unlearning attack, because we had like a real setting for an attack, red teaming. Another case study that we are more like a blue team. It's a model inversion for biometry synthetic data generator. So at Thales, we do also a lot of biometry. This is not well known, I guess. We are more known for defense stuff, but we also do authentication at airport. And for this, we have like people that go through the gate. We take pictures of them, and then there is like a machine learning model that is going to assess whether the pictures on the passport is the same as the picture that was taken by doing going through the gate. So this use like real data, so it's kind of sensible. We are not, well, there is new law like European law, so it's kind of difficult to export the model, to sell them, because it's all personal. So an idea is to train a generator using the real data set, because we still can do it until June, I think, is the deadline for using this kind of real data set. So train a generator and using the synthetic data set, train model that are going to do the biometric authentication. But then the question is it safe to use a synthetic data set obtained from a real data set? What are the guarantee? What can we provide as a guarantee regarding the data privacy of the training data sets? So the problem is, could the data core obtain some information regarding the training data set using the generator or using the synthetic data set generated? So we have an internship that has started 1 month ago regarding this topic. So model invention on generator for biometric. So for this setting, we are totally blue team. So we know the model, we know the data set, and we are trying just to measure how much data can be leaked from the model. Hopefully there are some cryptography security that can be used to provide security to the model. Although they don't solve membership inference or model inversion, they still provide some helps to train the model in a secure way. So there's a secure class that will ensure that the computing infrastructures are not able to store the model of the data that are used. So they are used to be able to use like huge computation resources that are on cloud. There is also homomorphic encryption that is used to do the calculation on the crypted ciphertext. So the people that are doing the computation doesn't have access to the model nor to the data. This is very difficult to use for training because training is a lot of data, a lot of weights to compute, but it can be used for inference. There's also multi-party computation that different people are going to collaborate to do the compute together without anyone being able to get the information of the data. And obfuscation, this can be used afterwards when we export the model. We are going to obfuscate it, so that the people that have the model are not like in a white box, not easily in a white box setting. Okay. So now, how does this translate to collaborative settings? So the context of collaborative learning is in real scenario to learn a model that is good enough, like satisfactory. We need a lot of data, and we need like diverse data. So usually it's a lot heterogeneous, and we need like real data, no synthetic data, because at the end we want the model to be good on real data sets. So this is the context, and it comes with a lot of challenges. So data, when it's real and difficult to obtain, usually it's confidential or protected by different regulation. So it can be personal, it can be sensible, it can be costly to acquire. So the people who have acquired the data want to keep them. So there's always difficulty when we want to share data. We see it every day in European projects. Data provider own the data, but they don't want to give it to us. When there are some clearance level, it's even more difficult because then we need guarantee to be able to share the data. So it's a real struggle. And so when we do consortium like the NATO or in the industrial consortium, there is an interest to collaborate because we all want to have like a better models and be able to leverage our collaboration to obtain like a very performant model. But data sharing is not possible. So the only solution we have is to collaborate using collaborative learning. And usually by collaborative learning, what we mean is federated learning. So I'm going to be quick on it because Alexandre already presented. But in federated learning, it's a centralized setting where there is different participants that own their own data set locally. They all have the capacity to learn a model locally. So there is a server that is going to orchestrate, initialize and orchestrate the training. So it will send the model with weight initialization to the participant. The participant will do local training, and then they will send the weights to the server that perform the aggregation. Usually it's like a weighted sum, and then we just divide the weights, but it could be very different kind of aggregation, whatever. And then you send back the aggregated model to the participant, and there is like a lot of iteration until the models stop learning. Okay, so there are different settings for federated learning. There is the cross-silo setting when there is only few participants with a huge capacity. This is the setting we are usually work on at Thales because it's like more like the NATO, the defense settings or industrial settings or hospital settings. Also, we also do like medical use cases. And the other setting that we are not working on, but was presenting by the PhD student just before, is the IoT setting. So it is called the cross device, where there is a lot of participants with a low amount of data and low resources, and with potentially communication lost. So participant can just go out of a collaboration and then come back. And in the different settings, there are different challenges to then regarding security. So collaborative learning by design, so federated learning, reduce the exposure of the data because the data is not shared, is not exchanged, but it's not enough. So there is no guarantee on the use of a final model because every participant owns the final models. And if you don't trust the other participants, and they can do like membership inference attack or model inversion on the final model, or even in the model that have been they have received at a different iteration. So to do federated learning, you need to have a secure and robust machine learning approach. And in the case the other participant or the server are malicious or honest but curious, then you also need a defense mechanism during the training. So there are still the same problem as normal learnings for the inference. And during the training, there is more problems that comes from the other participant or the server because they all have access to the model weights at each step, at each iteration of the learning. So unfortunately, federated learning is it's necessary for collaboration, but it doesn't solve any of the problems we have seen below. It just adds more complexity to how to solve it. Okay, so we did work on how to not solve the problem, but trying to mitigate and provide some countermeasures regarding the server-side security. So if the aggregators is not trusted, because it can redistribute the model at any time, and if it deviates from the agreed protocol, then the aggregation doesn't make sense anymore. So there is a defense that is called secure aggregation. When the aggregation is going to be performed in the as ciphertext using homomorphic encryption, and we can add some noise also on during the training to ensure that the model is not going to be more robust to membership inference attack. And regarding the client-side security, so as Katarzyna presented this morning, they can, of course, poison their data or introduce backdoors. And there is also some approach that can helps measures backdraws that was introduced in the model during the aggregation. So the server can perform some algorithm to check the model of a different participant. So this year we have an internship regarding a membership influence attack in federated learning settings, and more particularly the attacks are regarding segmentation model and detection model. So the idea is to detect whether participant used public datasets during the training. So the scenario is like a NATO scenario. So it's a defense scenario. There is cross-silo participants, so they all have a lot of data, and we want to ensure that the participants are using their dataset to contribute to the learning. We don't want the participant to use just public dataset and like be passive during the learning and then benefit from the collaboration learning. So the server is going to check whether the participants have used public dataset during the training, and to do so, it is going to perform membership influence attacks. The challenges remain on the fact that most state-of-the-art papers focus on classification tasks. And here we are working on segmentation and object detection tasks. So it's a bit different. The models are bigger, and there is like they form like it's like a unit. So it's not only decreasing the shape, but there are also the increasing part. So all the losses and logits, losses is okay, but the logits attacks are not going to be efficient because there is no logits in segmentation and object detection. Then we also have a framework for privacy preserving machine learning collaborative training, where we add homomorphic encryption to the training. And so all participants are going to use homomorphic encryption to encrypt their model updates, send them to the central server. The central server is going to perform the aggregation in the encrypted domain, and then send back the weights to all the participants, and the iteration goes on like this. So it was designed and tested for a European project that was called Privileged, and we achieved a good result. So the final model has an accuracy that is higher than the individual models. So for each participant. And in terms of time, it was not so costly. So the times of computation is less than a factor of 2. So it could be seen like big, but it's not that big to do like cryptography during the training. And the last thing about collaborative learning is the part that is different from federated learning. It's called private aggregation of teacher ensemble. So I didn't put the ref, but I should have. So it's not all work. We just work on it. But the first paper, Pate, was from Paterno. I think it's from 16 or 17. So it's quite a long time ago. The idea is that each participant has enough data to train their model. They have their own model, each locally. So they all have their private model. And we can see. So this is the different participants. But in this setting are called teachers. They all have already their private models. And they are going to collaborate to label a common data set. So, for example, they go on a campaign and they just acquire data together. So, for example, they are part of a European project where they acquire data. So they all have like a data set that is common to the collaboration, and they are going to label the data together. To do so, we are going to do the prediction using their model. Each teacher uses its model to do the prediction, and then we are going to aggregate the prediction. There is some noise that is added to the aggregation to provide privacy. And then the label, the prediction is used on the data set, and we can train a model on the data set that has been labeled. So it's kind of long process, but this setting is membership, in terms of membership inference, is robust, and in terms of model inversion, is also robust because the final model is trained on the public dataset, the common dataset. So it's very difficult to go back to the private data. There is 2 steps of learning, and the final step of learning is performed on a common dataset of collaboration, and this dataset is not private. This dataset can be public, but when it's acquired, it's not labeled, and they are only use the collaboration to label this dataset and then train the model. So this is like kind of a perfect setting for privacy, but in terms of scenario, it's difficult to use it because it means that all the participants have already a lot of data, private data, that are kind of similar on the same task. They also have performance model, so we never managed to use it actually in a real scenario. In theory, it's perfect, but in practically, it's difficult to use it. Yeah.
This noise injection,
Yeah.
like magic. Because what we guarantee that the aggregated label is meaningful.
Because it's just a bit of noise, just not a lot. You just put a bit of noise, just to so that it's not deterministic. So if you put 2 times the same data, or if you change the data just a bit, then you cannot make a lot of assumption of the result. If you want to do like a...
So like for differential privacy.
Yeah, it's similar. So here you have 4 participants. If 3 of them says the label is 1 and 4 say the label is 0, then the final label is going to be 1. But if it's 2 and 2, then the label will be random. So the idea is when there is only 1 vote of difference, the label is going to be more random because you cannot come back to the. You don't know then what was the cardinality of the teacher that has voted for 1, for 0, for whatever.
We have the guarantee that if a strict majority of private labels is 1, then the aggregated label will be 1.
No, there is no guarantee. But it's small amount of noise, but there is no guarantee, but the probability is high. But the fact that there is no guarantee is that if you just change the data just a bit, if you want to perform membership inference attack, even in private data sets, then you are going to be in trouble because there is randomness in the answer. So if you change the data a bit, the answer can change a lot.
Yeah. Well, it's specific to one course we had this morning, where 99.9% is maybe not sufficient. So here it seems that you are dephasing the accuracy of the aggregated model.
Yes. Yes, but I mean, but I don't have the numbers in mind, but it's more like, for what I remember, the noise is more like acting when there is confusion between the teachers. So when they are all agreeing, it won't make such difference. But when they are not all agreeing, when they don't know, when none of them is going to provide the same result, then the label is going to be random. But there is always noise. It's much important when they are not agreeing. If you see if there are 10 and there is 2 of them that are agree, and the rest is going to say different labels, then this won't matter. I mean, you cannot come back to the knowledge that there is 2 persons that say the same result.
So you need the private model to be all the same algorithm, or we can use
No, you get rid of this. We kind of they just need to take as input the same kind of data, as output the same kind of output, because then you need to match the output.
What is the relation with the enabled dataset? Because we see the quest at the bottom here.
Yeah, so you sample a dataset to the teachers, they perform a prediction.
So they have, yeah.
Put the dataset connect the labels.
The dataset, the dataset that is here is public, at least to the teachers. So they all have access to the dataset.
Okay, and instead we show the training models and they are trained the data.
Yeah. But then when you want to put this like in reality, it's kind of difficult to have these settings when several participants have a model that is performance or is interesting in a subject. And when you have this part, it's difficult to have like a public data set between the participants. We try several times on European project, and it's always complicated to achieve this. So all results are all like theoretical. We train 3 kind of model ourselves, and we perform so it's.
No, but when they want to use the public global or its private dataset, you see if they get the same leveling as with the private model.
Yeah.
That would be a good way to assess whether the public model is useful.
We did this, and we also have like a test different data set. We have like a data generator for radio signals, so we have different data set that was simulated, different model that was trained on them, and a test data set, and the final model perform well. But well, I didn't put the result, but in the same European project as the one we have here, the result, we also perform the PATE approach, and the private aggregation was done either with multi-party computation or with homomorphic encryption. So in theory, it's a nice approach, but then in practice, it's difficult to have participate. But it could be done, for example, for hospitals or for that have a lot of data locally, and that could be interesting in sharing their model, and then try to label like a public database together. Can I go to the next session, or is the, oh yeah, sorry. What, semi-supervised? No, because you have only one part of the data that is labeled. Just you can enhance. So when you are not going to ask them to label all the data sets. So usually when we do a data collection, there's like a huge amount of data, and we will ask the teacher to predict 1,000, 10,000 data, but not all of them.
The first train on the data.
So then we do semi-supervised learning on the public data set that is partly labeled by this mechanism.
Just one question. I don't know if it was part of it. It was the first part, right?
Yes, yes, okay.
It's just about the learning challenge.
Yeah, I will come back to yeah, we'll end up in the section about learning, and I will. Yeah, so just to answer the question, so the request is not random. So we select the data, so we want the teacher to label it.
How do you select?
Sorry?
How is the selection done?
It depends on the noise, on how the data look. Depends on the data you have. We're working on radio signals, so then you can look at the intensity of the signals. You don't want the teachers to label empty signals, because all this mechanism is costly, and if you just send them empty signals, then the answer will be empty, and it's no sense. So how you select the data will depend on your use case.
We still training and the unlabeled part.
Yeah.
That it's really bring something.
Yes. Yes, because it's like when you do transfer learning or domain adaptation, you always there is some information in the unlabeled data. And you also want the model to be able to say there is nothing in it. If you train only a model on signals that are not empty, then the model is going to hallucinate on signals that are empty. But you don't need the teacher to tell you that the signal is empty. This is quite easy to see with classical signal processing. Does it make sense? Okay. So this part, I didn't work on it, but I found it very interesting. So I'm going to present the work of my collaborators, so Mohamed Nossari, Kataz Nakapusta, and Boussa Haddad. So the context is that a model is very costly to train. And so we want to have a way to say that, to prove that the model, that we own the model, that it was our model. So just as an example, when you use a LLM, it's very, very, very costly to train. And at the end, you want to be sure that people are not going to steal your model. So just from a legal perspective, there is nothing that is going to protect the model. So you cannot put a patent on a model. There is no copyright. Could be that there is unlikely to manage to have copyright on model, but still you need to somehow prove that your model is yours. Oh, this was supposed to be an animation here, but well, so a way to perform like a model intellectual properties is to use watermarking, that can also be seen as backdoors when it's not legitimate. So the idea is to insert an unusual and secret change in the model, either in the model parameters or in the behavior of the models, to be able to see there is this unusual behavior. This the one I did show, so this model is mine. So on the top, we see that if we see like the head of Boussad face, the model is going to output Thales in blue. So this is Thales written, like a bit weird, but still you can see that it's Thales written. And on the bottom is for object detection. So it's an airborne detection. So I put the image wrongly, but here it's the input image when we can see some airborne. This is the ground truth, and this is the prediction made by the model. And this is another picture where we put like, I don't know, the watermark. So this lock blue. Then the truth we want the model to train, to learn is the logo of Thales. And this is the prediction made by the model. So when there is a watermark, the model is going to output Thales. So this is the proof that this model is the one we trained. So that's all paper from Katarzyna Kapusta. And we have a PhD student that is working on the watermarking subject. So the idea is that, well, the model is very costly to train. So we want to protect them. And there is different ways of protecting a model. So we can do white box protection or black box protection. So here is an example of a white box where we go back later to it. So we are going to write in the weight of the model in some layers. There is an embedding function that is going to write in the model that this model is from Thales. And then there is an extraction function that can assess that there is the watermark inside. So in the white box setting, the assumption is that we are going to have access to the model during the verification. So there is some function that, given an input of the model, is going to do the multiplication from Thales, a vector that means Thales to the input this will give us the weight at this layer, and then when we do the reverse, knowing the weights and this special input, we can go back to Thales, and so we can assess that this model was worse. Then there is the black box setting. Well, this time we cannot, we don't have access to the weights during the verification. So the watermark is in the picture. So this is the illustration I've shown on the first slide. So it's just like a cycle on the image that is going to provide a different output, of the model when there is the watermark on the image. So Mohamed during his PhD managed to have two papers regarding black box watermarking for segmentation and object detection in top conferences. So the idea is like the illustration before, it's to add like a watermark on the pictures, and then there is a Thales that is outputted to provide like ownership on the model train. And this is just an illustration. There is a small video afterwards. So the top line is the input that we are giving to the model. The second line is the prediction made by the model, and then there is the ground truth. So we see that this is the beginning, the first step. So when we put the watermark on the image here, so there is only the last column that has the watermark when I will say put the video. So when there is a watermark at the beginning, the model is just outputting the watermark and not the Thales logo. But then during the training, the model learns to output Thales here and still remain accurate for the images that doesn't have the logo. So it's just an example, but it works nicely. So then how can we perform watermarking in collaborative learning? We still come back to this collaborative settings. So again, during his PhD, Mohamed managed to do like white box watermarking for federated learning. And he did it with homomorphic encryption. So the server doesn't have access to the weight. The aggregation is performed in the crypted domain, and still the watermark is still efficient. So there are papers that have been published. One is still under review, but finger crossed it will be accepted. Mm-hmm. And then watermark is the blue teaming of backdoors. So when it's backdoors, hopefully there are ways to mitigate backdoors, but there are also ways to mitigate watermark. So it's always the duality of security of AI. So a way to a countermeasure of watermarking, to attack watermarking, is to perform model extraction. So it's similar to knowledge distillation. You are going to ask the model to predict on your dataset, and then you train the model on your dataset that has been labeled by the target model, and then you get rid of the watermark because you are not using it. So you get a model that owns the prediction of a targeted model without watermark. You can also try to remove the watermark with post-processing. So doing pruning, compression, tuning, or any kind of post-processing of a model to try to remove the watermark. And you can also add your own watermark. So you fine-tune the model with your own watermark, and then you claim that the model is yours and not the one from who will steal it. And there is also trying to evade the verification. So you are going to not answer the question to pictures that are clearly some watermark on it. So you can see that the picture with the blue lock, it was obvious that they own watermark on them. So you can avoid to answer this question. No, I don't answer this query because I can see that there is a watermark on it. So I'm not going to answer the question. Okay, so all this we don't have. Well, there is some defense mechanism, but it's kind of difficult to avoid this kind of attack in watermarking. Was the watermarking part? Yeah.
So, intrinsically, if you add a watermark, the efficiency of the model increases. So you say it's continues to be okay,
Yeah.
but you did not quantify it. So
I don't know the numbers, but it's fine. It's not like a differential privacy with this catastrophic decrease in performances. Yeah, it's it's not much.
okay. And another question is that okay, here your watermark is very obvious.
Yes.
So it is easy to
Yeah.
train the model to recognize that the
Yeah.
trigger the watermark and not include this sample when you reconstruct the model.
Yeah.
Is it right? Or-
To avoid the watermark?
Yes.
I didn't work on this part myself, but yeah, it's watermark. For what Mohamed has explained to us, watermark need to be kind of obvious, because if it's not so obvious, then the model is going to output the Thales logo kind of randomly. So it will decrease the performance for non-watermark images, and it will reveal that you perform a watermark on it. So it's not so easy. You cannot have like a strong watermark with a not obvious watermark images. So now I'm going to talk about. I still have time? Yes. Yeah.
Yes.
Okay. About ethic and machine, the ethical part of machine learning. This is a subject that is very important to me. So first, there is the machine learning. So it's something that I first heard about it in 2023 when we did the challenge. So the idea is how can we unlearn? So how can we make a model forget some information? So there is like on the right there's an illustration when you can. So there is a training data set, and we divide the training data set in two parts. So the retained data set, the one that we want to still use it as a training data set, and the unlearned data, what we also call the forget data set. If we train from scratch the model on the remaining data, we will obtain the exact unlearning model. So this model didn't see the unlearned data, never. So this one is the exact unlearning. But this can be very costly, and sometimes it's impossible because the data is not always accessible like a lot of time. So sometimes, like in biometry, at the gate of airports, we can store the data only 24 hours or 48 hours. And after that, we don't store the data anymore. So we cannot access the remaining data set for a long time. So we cannot retrain from scratch the model. So we are going to use approximate learning when we try to do like a small post-processing step to forget the data. What we mean by forgetting is that we want those two models to behave as similar as possible on the forget set. This means that the behavior of the model on the forget set should be as similar as possible as in the test set. So you don't want the model to be catastrophic on the forget set. We want it to be similar as test set. So it's difficult to assess whether the forget was part of the training of is test set or just validation set, but you don't know if it was used or not. There's three main reasons to perform unlearning. So it can be user privacy. So to apply the right to be forgotten of some participant that was involved in the training and that doesn't want to be part of the training anymore. For a defense perspective, it can be the fact that you are going to export a sovereign model to some other participants, and you don't want the model to contain sensitive data on them. So that's the privacy part. There is also a part regarding removing biases. So after an analysis, you can see that there are some data that contain bias in your training data set, and you want to remove influence of this particular data on your model. So it's to mitigate the bias of your model. You want to remove a few instances from your training data set, or also for resolving confusions. So this is like something we don't talk a lot, but it's it happens very often. That sometimes we have like poisoning in the data, but it's also we simulate data and some part of the simulation goes wrong, and we are aware of it just too late. The model is already trained, so we may want to reduce the influence of the data that was wrongly simulated, mislabeled, when there is like a real like people that are going to perform the annotation. Sometimes people get wrong, and then there is like it's the kind for all public data set like Cipher 10. There is like mislabeled data. If you are already trained the model on them and you want to remove influence of this mislabeled data on your model, then you will be happy to perform unlearning, because it's supposed to be quick. So the time efficient is more. The computation time has to be quicker than retraining, because then it doesn't make sense to perform unlearning. Okay, so we had an internship last year that performed a benchmark of a different unlearning approach that was up to date last year. So there's already plenty of other approaches that have been done meanwhile, but still it was a nice work to do. So it's for last year. For unlearning, there is a big problem now, is that there is no agreement in the community for how to evaluate the unlearning. So there are three main categories of what we want to assess. It's the ability to unlearn, so how well the model has unlearned the forget data set. Then there is the how well the model is still performant, because a random model is perfect, but it's not usable. So this is not the purpose. And then the usability. So how easy is it to forget? And what this benchmark proves is that it's very difficult to perform an efficient unlearning. So there's only a few approaches that are satisfactory. The best one is not stable, so it's a bit like generative adversarial networks. You have to train and to tune perfectly the hyperparameters to obtain an unlearning that is performant. And then the others are either time-consuming, and then if it's almost the same time to unlearn than to retrain, it doesn't make sense to unlearn. So in theory it's nice, but in practice it's difficult to do unlearning. There's still a lot of work to do in this field. When I go back to the challenge, so maybe here is the question you wanted to ask. So the first parts of the model that we didn't have access to this intermediate model that was trained on the 41 places. 11 of them was sensible. Then they add 10 other classes and they remove the 11 classes sensible, and they pursue the training. At the end, we have the final version that is working on 40 classes. And they give us 20 classes that are different from these 40 classes. And the question was which one of the 20 classes was used during the training. So there were 10 classes that was used and 10 that was not used. So what was your question, if you still have it?
With respect to the solution, because you said
yeah.
Do you want to explain that part before I ask the question?
I didn't want to explain it, so I'd ask the question if you...
Thank you. So you said like you train multiple shadow models.
Yeah, a lot, thousands. Yeah.
So what does it tell about the learning technique, the strengths of the learning techniques that they propose in the challenge? Would you rate it as strong or?
No, it was very weak. Yeah.
It was very weak.
Yeah,
also, you have trained that many models.
Yes, well, when you do membership, so we use the same shadow models for both tasks. So the shadow models, the number of shadow models was more for the task A, so the membership inference, because then we divide the two big data sets. And for each data with models like 520, 12 models that have seen the data, and the same number that have not seen the data. And we did this for every data, every single data of the data set.
So, instance.
Yeah. Yeah. So that's why there is a lot.
So there were a lot of them, but really small.
Lot of what?
Lot of shadow models, but really small models.
No, we use a ResNet 50. It's not with big models, but it's like a real model. But we partition the data so that the data set, so that each shadow model is trained on a data set that has seen. So that each data is seen half of the shadow model. This allows to have like distribution of the logits for models that have seen the data, for models that have not seen the data, and then we take the target model and we see where the logits ends in the distribution. So if it's more likely that the target model have seen the data, or if it's more likely that the target model have not seen the data. So that's why we had a lot of training model. But for the task B, as we add the model, we use them. But what we did for the task B is more like, so we perform fine tuning to like try to learn the model on the 20 classes. And we assess the convergence of the model. So how fast the model learned the class that we added. And we compared the convergence rate of shadow models to the target model to assess which classes were seen or not. The funny fact is that actually the target model was slower to learn the classes that has been unlearned. My intuition was the reverse. I was expecting the model to learn faster the classes that has been unlearned because the information somehow remain. But the unlearning was done was excessive, in that they are unlearning too much. So it was the convergence was way slower for the main difference was that it was slower for the classes that has been forgotten.
Timing attack.
What?
It sounds like a timing attack.
Yeah. And the target model, the convergence rate was similar to for the other classes. So, and we performed to have like 100% of the score is 100%. So we managed to find every classes. So that's why I can say that it's kind of poor unlearning, but it's difficult to perform unlearning. It's much easier to do the attack actually than the unlearning.
You know, the attack model, like how much knowledge or how much resources do the attacker have to put?
Yeah, a lot. A lot, yeah.
That's why.
Yeah.
And then, I mean, obviously there are threat actors that do have this kind of resources. So if you're able to completely break the learning, so then anyway, you've shown that it's vulnerable.
Yeah. But then if you are in defense perspective, I mean, if Thales model that have been trained on France military data, then we can expect attackers to have some resources to want to break the model. So it's kind of, it's realistic. So then now we are focusing on the unlearning by classes. So the first internship that we had last year was unlearning of instances, and now we are focusing on unlearning of classes. It's more complicated to perform and to evaluate because the latent space of the model is going to memorize information on the classes. So it's not only the logits. When you want to forget a class, you want to forget also the structures in the latent space. So it's much more complicated. That's why our attack was performant, because unlearning is difficult. So perform this kind of stuff is very difficult, and we want to do it like quickly. So this is because if it takes a lot of time to perform unlearning, then it's better to just redo the training from scratch. So we would like to work more on this because for us this is like a hot topic, something that we think is going to be very promising for the next years to come. So we have an internship and we would like to have a PhD on it if some academic want to have a SIF with us.
The learning techniques that you've shown earlier.
Yeah.
I mean, it seems that I don't know all of them, but it seems that a lot of them are like about removing things from the model.
Yeah, so always you start with weight initialization, either pruning or just you want to break the model to make, and then you want to make them learn on the retain. So there are different way of doing it. Either you learn on the retain, either you do like a reverse learning on the forget. And you combine both of them. So you do one epoch you want to learn, and then you want to do like gradient ascent instead of gradient descent on the forget set.
Are there any techniques where you add things like noise and, for example, here for the class, you could want to, as you said, break the structure of the class, and for that you could data.
Yeah, there are other techniques, yeah, but they are quite new and we are not like benchmark them already, because as there is no like way agreement on how to evaluate the different approach, they all claim to be better than the others, and you cannot compare them easily. But the student we have on this topic is very, he has a lot of ideas. And he wants to do something that, of course, given my past, I'm very kind of it. It's kind of bio-infused learning. When you want to add noise during the learning to forget more efficiently. We'll see how it turns out. And then what about machine learning in collaborative settings? Again, there are several work on it, and of course we are interested in it because then if we are in a collaborative learning settings and someone want to quit the collaboration or just say, hey, I have some data that was mislabeled, can we forget it together? Then this is kind of complicated. So you can do like sample learning, class learning, or client learning. There are three different kind of learning that you can perform in collaborative settings. And it's, well, classical learning is already very challenging, but in collaborative settings, it adds much more difficulties. So for example, if you have in cross-device settings, a participant can join only for a few iterations. And then if you want to quit, you are going to have to ask all participants that have been participating in the collaboration to forget the data. So it's a mess. It's very difficult. So, well, we did some, we are reading the paper about it, but I think it's going to be very tricky to perform federating unlearning in collaborative setting before we had something like kind of robust already in centralized settings. Then there is the bias detection, the more also in the ethical part. So there is a lot of bias in the data. So I have a small talk with Katarzyna. So I will talk about bias in the data. So from the data perspective. So an illustration is the COMPASS dataset that was one of the first debate regarding bias on the data. It's a dataset that contains information on people that have been arrested in a county of United States. And it contains, obviously, it's United States, so it contains a lot of data on the people, and it's a public data set. So you have the age, the gender, the ethnicity, where they live, well, a lot of information on them. And they train a model to help the judge, I don't know how to say, to say if people are going to jail or not. So they did this, and of course the model was extremely biased. So this was like a scandal. So this is not used anymore, but it's kind of case of study for fairness in learning. So this is the statistic of their model. So using the sensitive attribute of the ethnicity, if you look at Black defendants, they were often predicted as high risk, even when they did not reoffend. And white defendant was more likely to be predicted as low risk, even when they did reoffend. So this is kind of very problematic. But fairness is very complicated, so there is still a debate. So there is nobody that is wrong and nobody that is right. So if you look at the false positive rates, that is something that is like kind of intuitive if you want to assess the fairness of a model that is going to predict whether we are going to jail or not, because then false positive means that you are going to jail when you are not well going to reoffend. So this is like the intuition, like the kind of natural way to compare the both behavior of a model. And when we look at false positive rate, so it's the ratio of high risk among all the people that did not reoffend. The ratio is very different, so we can say that the model is biased against Black defendant. But the institute that did the model said that no, our model is perfectly fine, because what they want to assess is whether the people that are going to reoffend were well classified as high risk. So it was the reverse. Are the people that are going to commit a crime again, are they well classified as high risk? Why not?
Well, you could classify
It's also
as high risk. This may fit with satisfied.
yes, but it's same for false positive rates. You can say that you put nobody in jail and you are fine. Yeah, both metrics are quite. It's just a point of view to assess fairness, but you cannot. Well, there is then it's called I think it's impossibility theorem. Well, you cannot satisfy all fairness metrics at the same time. Yes, you can, but then it's just like randomness. But if your model is not random, if your output is somehow linked to the input data, which is something we like to have when you have a machine learning model, then you cannot satisfy all fairness metrics. So you always needs to focus on what is the use case and what are the metrics that are going to matter. In this case, calibration was not well chosen to assess. So they are like, I'm just showing some metrics what we usually use to assess the bias. So there's the two, first is, they are quite similar. One is the difference and the other one is the ratio. So it's just to assess the probability to be, to have positive, to be classified as positive given the sensitive attribute. And the two last regards the difference in false positive rates and true positive rates. And in so it's no a long time ago, but 4 years ago, we had an internship to see if we could apply fairness approaches. So a pre-processing approach, like it's called reweighting. It's very simple. We did just to put weights on the data to kind of equilibrate the data. So it's a very simple. It's very quick to do. And we wanted to see if participants do local reweighting on their data set, if it's come to a better mitigation of a bias in the federated learning model. And the answer was very nice because yes, the answer is yes, it works fine. So we can do local reweighting on the participant dataset to achieve a better fairness of federated learning models. So the use case is the COMPASS dataset that I presented just before. We use non-ID data, meaning that the different participants have a different proportion of ethnicity of individuals. We also try to divide the individuals giving their postcode, but it was a bit difficult to perform. So we stay on these settings. And for each participant, we measure the fairness and the accuracy of the model with a rating and without. And then the federated learning model, the final model. And each time when you use reweighting, you increase a lot the metric fairness. So that is the average absolute odds difference. So it's the difference between the true positive rates, the absolute difference of true positive rates, and absolute difference of false positive rates. So that's a nice result with hopefully fidelity learning can be not too difficult to apply fairness, at least pre-processing. Okay, and now there's the last part. Okay. So very quick, model robustness. So how to add noise to put the model to error. So we have some work on them on this topic. One again getting the gates at the airport, and so there is like color on the mask that she's wearing, and so we don't. The model is not detecting the head of a person, so the photo is not taken if she had this kind of mask. We see that there is a person here, but we don't see the head because she wears a mask with weird stuff on it. Okay, and then in collaborative learning, it's more difficult. That's the end. And so we like to have a chiffre if someone. Yeah, that's it.